back to Limp Bizkit for a minute. Rolling objects have both translational and kinetic objects. An object that is rolling will have both translational kinetic energy and rotational kinetic energy. There are two modes of rolling. There's rolling with slipping and rolling without slipping. Rolling without slipping means the object does not slide or skid as it rolls on its surface. The rotation and translation are synchronized, so the atoms of the rolling object stop at the movement they come in contact with the surface. When an object rolls without slipping, we can use the equation V equals omega times r to relate the center of mass speed v and the angular speed. We can also say that A equals alpha times r to relate the center of mass acceleration and the rotational acceleration. The friction that acts is static friction, so we can't say frictional force equals mu times Fn, because static friction is always less than mu times Fn. Remember, static friction has to first be overcome to turn into kinetic friction. Static friction cannot dissipate energy. So if an object rolls without slipping, no energy is lost to dissipated forms. Meanwhile, if we are rolling with slipping, the object peels out, skids, the atoms slide against the surface, rubbing against the two surfaces together. We cannot use these two equations because the rotational and translational motions are not synchronized. If a wheel is peeling out, spinning a lot but not translating a lot, then V is less than omega times r, not equal to it. If a wheel is skidding, which is not spinning very much but translating a lot, then the velocity is greater than omega times r, not equal to it. We can use frictional force equals mu times Fn because if an object slips, the type of friction is kinetic friction. That is such an important thing to have just stuck in your brain. If you're rolling without slipping, then you have static friction. That's the wheel coming in contact at just one point. And if you have static friction, you're not dissipating any energies. If you have kinetic friction, then the wheels are now stuck in place and they're rolling along. So that means energy is being dissipated in the forms of heat and sound, as usual. Look at this. We've got a block of ice with no friction in the bright blue block on the left, a disk with a low rotational inertia, the green one in the center, and a hoop of high rotational inertia on the right. All have the same mass and are released from rest at the top of identical inclines. The disk and hoop roll without slipping. You probably already see that the ice wins because it has no rotational inertia. The hoop comes in last because its rotational inertia is the greatest. But why does this happen? Thinking about energy principles. So you've got these white marks on the places where the four bright colored marks on the disk and hoop touch the line. Here, here, here. And you can see there's light marks on the disk the disk and the hoop that are coming in contact with these white spots. This is going to be important in a second. First, all three objects start with the same gravitational potential energy, same height. If you have height, you have gravitational potential energy. Look at your charts at the beginning once it resets. Ready? Ready? Boom! Full! All gravitational potential energy is the same. In all three instances, the gravitational potential energy becomes kinetic energy in one form or another. For the ice, all of the gravitational potential energy becomes translational kinetic energy, so the ice has a higher speed at the bottom of the incline, 1/2 mv squared, right? All of the energy is converted into 1/2 mv squared, which means it has a greater velocity. Frictionless. Block, greater velocity. The greater rotational inertia, the more gravitational potential energy is going to be diverted, stolen, taken away, something like that. It still remains in the system. It's just doing other things. Rather than moving the object forward, it's also having to overcome this rotational inertia to get the object rotating. So as you can see, that's going to leave less translational kinetic energy right here, which means the translational kinetic energy is the lowest, so that means the speed is also the lowest. Meanwhile, over here, you're losing less translational kinetic energy to rotate the object. This is why the hoop loses. The hoop has more rotational inertia. Has more rotational inertia because all of its mass is spread far out from the axis of rotation. The axis of rotation is directly in the center, and all of the mass is further away. Meanwhile, the disk has some mass closer towards the center. Let's say all three objects have mass m and start at height y on the incline. To find the speed of the ice block on the bottom of the incline, we're going to be using just conservation of energy. All of that gravitational potential energy turns into kinetic energy, right? mgy equals 1/2 mv squared. M cancels on each side. We get that good old v equals square root of 2gy. Now, to do conservation of energy for an object that rolls down the incline, the object starts at height y, has mass m, radius r, and rotational inertia I equals some constant times mass times the square of the radius, or the distance from the axis of rotation, more precisely. The system starts with gravitational potential energy, mgy, ends with a combined kinetic energy, translational kinetic energy, and rotational kinetic energy. So, that's what we have. Remember, total mechanical energy. All of the energies in the beginning have to equal all of your energies in the end. No big deal here, right? Because the object rolls without slipping, we don't have to worry about energy being dissipated. So we can also say that v equals omega times r, which gives us omega is v over r. So without even needing our angular velocity, because it's not given to us, we can just substitute in that v over r. There's our energy equation, conservation of energy equation. We've got a mass in 3 terms, so that's going to go away. R squared, because we have R squared in the numerator, R squared in the denominator, so those go away, and factor out V squared and 1/2 on each side, and we are left with solving for V to be V equals square root 2gy divided by 1 plus k. The 1 comes from factoring out that 1/2, pulling it from each side. If you don't do that, it's still going to work out algebraically. Don't you worry. It's just a little bit harder to combine. What does this tell us? The speed an object has at the bottom of the incline depends only on the incline height and the shape of the object. And gravity. There has to be gravity, otherwise it's not happening. Is gravity accelerating these things down? No, it's that parallel component of gravity, right? You also have to worry about the angle that these inclines are at. If you have a steeper angle, that's going to affect your height. So that's kind of just implied there. The speed does not depend on the object's mass or its radius. A greater height means greater speed at the bottom in all 3 instances. A larger K means more atoms on the outside, reduces the speed because this makes the wheel harder to rotate.